Okay. Right. So, yeah. Oh, not homework 6. Okay. What questions do you guys have? Last homework, using the natural log to solve. Okay, so you're talking about problem number 4. So I think that's the only thing that uses natural log. All right, so I mean, feel free to like unmute yourself also. It's slightly easier to communicate that way. But are you stuck on like the step from here to here where I'm actually taking the log?
I'm having more trouble with like part B.
Part B. Okay, yeah. So you take the log, and then is it that you couldn't quite follow this expansion? Going from here to
Like
here.
what like once you get past the like expansion, like
Mhm.
to get to the f prime times 1 over f of x.
Yeah.
Once you get from there to there is and then is where I'm having a bit of trouble.
Okay. Um. Well. Okay. So, but you agree with like the um left-hand side, right? That's pretty much something that I had told you about. And then I'm just taking derivatives for each of these. So so notice like the derivative of the natural log function is just going to be 1 over x. It's going to reciprocate the function inside the natural log. So that's why we have these denominators that are exactly the same thing as what's inside the log function. But then we have to tack on a chain rule. So, and then the chain rule gives us what I'm boxing here. So these things are coming about from chain rule. And that's how we get all 3 of these terms, really. Well, the second term is kind of easy. Does that explain your question?
Yeah. And then I'm also having troubles with finding the derivative of e to the power of like something with x.
Okay. Yeah. Yeah. Uh, e to the something, basically. And the thing is that you're not quite sure about this. So the rule is that for just the function x, e to the x, you have the derivative rule that it's the exponential function itself, right? You want to think of the exponential as a function. So actually in math, there's sort of a notation that's a little bit more convincing that we think of this as a function. This exponential exp is what we call it. So we're exponentiating the stuff inside. Here we're exponentiating this f of x function. And the way this works is, well, the derivative of the exponential function is just going to be recopying itself. And then we look inside the exponential function. Actually, let me also write like what this would be using that notation. So it's the exponential of the f of x function. Okay, so that should be more convincing. And now, well, chain rule says we take the derivative of the inner function, and so that is f of x, well, f prime of x being multiplied. So this guy ends up being your answer in general, right? And so hopefully that explains that. Does that resolve your question?
Yes, thank you.
Okay, good. All right, other questions, other things you want me to go over or do?
I have 2 questions. And my first question is, so it says, like in the directions for the exam that if we have questions, we can ask our instructor. Would that be you that we would email and ask questions to?
Yes, it's me. Yes.
Okay,
Instructor
perfect.
meaning like recitation instructor. Yeah.
Okay. I
Yeah.
wasn't
But
sure.
Right, but for this, I'm gonna have to like check what type of questions you're asking me and make sure you're not just feeding me the problem. Like I'm only gonna be able to answer things that are more like clarification based. So yeah.
And my second question is, would you go over the squeeze theorem?
Squeeze theorem. Yeah, sure. How do we want to do that? Hmm. I mean, I could probably find, or I could just write it. Right. So the idea of squeeze theorem is that you want, how do I put this? Squeeze theorem is used to solve some kind of a limit. The idea is you're given some limit and you want to evaluate this, but you have sort of restrictions on what you're able to do with this limit. And if you have like some information about the function, namely that it's bounded above and below by other functions, so we'll use g and h for x in an interval containing the number a that we're trying to limit this to. So as long as we actually have that f, the function f, is sandwiched between g and h, and that we can actually take the limits of these other two functions that bound. So if we can actually take these limits as x goes to a and limit of h of x as x goes to a, and if we get the same number, so say that this gives us some number L, and the other guy should also give us the same value L. Well, since this inequality held true for all x in the interval containing A, that means that this in the limit is also going to be sandwiched or squeezed to take on that one value. So we get that this, I guess, must be L is what I would want to write here. So must be L as well when you take the limit as x goes to A. So sort of schematically, this is what squeeze theorem is saying. And then the typical way that you see this used in practice is with the function of the form sine of 1 over x, I think. Well, no, you normally have like a function in front that sort of bounds the behavior. So like an x squared, an x to the fourth. Normally you're given x to an even because then it splits up nicely. If it's x to the odd, it doesn't really split up that nicely, although you can still actually do an argument with that. The reason for that, for this kind of function, is because you can't, the sine of 1 over x function doesn't actually have a limit. But when you put that x squared in front, that gets rid of the infinite oscillations. So yeah, the original function without the x squared, that limit would not exist because it doesn't tend to a specific value. It oscillates infinitely fast as you approach, oh, this should be 0, not a, 0. Make that clear. And so what's important is that with this kind of function, you have the property that the sine function overall, what you know about it is it's bounded between -1 and 1, right? If you just think visually about the sine and the cosine function as well, you could say the same thing about cosine. These are oscillatory functions. They bounce up and down like this infinitely, but they're always bounded between, trying to draw as carefully as I can, always bounded between 1 and -1. So they never exceed those two limits. And those are the functions more, well, we would then take this inequality and then scale it by this function that's in front. and that would give us our g of x and our h of x. So for this particular problem, what you would do is you would bound it by the limit as x goes to 0, x squared. Also think there's a times 1 there because really we're multiplying this side of the inequality. And it's bounded below by a negative x squared. The negative is coming from this -1 here. Maybe I don't really want to write that. Yeah, so bounded above and bounded below, okay, by negative x squared and x squared. And then when you take these actual limits, well, this guy is going to give you 0, this guy is going to give you 0, and so you can conclude, therefore, I don't know if I showed you the notation for therefore, but for us it's like a 3 dots is the notation. I don't really want to use the inequality there, but yeah, so therefore this guy gets squeezed into being this one value, 0. Does that explain squeeze there for you?
Yeah, it helps a lot.
Okay, great. All right, other questions? Question 1, part C, last homework. Okay. Question 1, part C. Yeah, this guy. Okay. So the first thing that I did before I tried to take the derivative was I noticed that you can simplify the function a little bit. And the reason to do that is because if you can at all simplify your function before you take the derivative, you should try to do that. Because well, it's just going to make the process of taking the derivative slightly easier. Here, what I did is I remembered the log rule, which says that if you have an exponential, or well, if you're raising to some power inside the log function, you can pull the power out. So the w squared, that 2 comes out. Okay, and that does simplify things because you would rather take the derivative of this 2 ln of w as opposed to this ln of w squared. Derivative of ln of w squared is going to have a chain rule tacked on. It'll be 1 over w squared times 2w, but it goes to be the same. So then what am I doing? I'm doing a quotient rule, and I wrote quotient rule off to the side here. Okay, so you just have to remember you take the denominator, tangent, times the derivative of the numerator. So then in these parentheses, I'm taking the derivative of the whole numerator, and well, derivative of 2 ln w is 2 over w. This is a log function over a different base, so we have the 1 over w, but in front of it we have a scaling factor of 1 divided by the log of whatever the base is that we're working over. So this is the generalized version of the derivative rule for logarithm. So this guy is that derivative of that log. And then rest of the quotient rule says minus numerator times derivative of denominator. And so here's the numerator, here's derivative of the denominator. You just have to remember, or I guess in the case of this semester, you can hold on to a table of all the derivatives. You're allowed to use notes, which is going to be different than every other semester. Yeah, tangent is secant squared, take the derivative, and then of course divide by denominator squared. Yeah. So that's how I did part C. Could I make a formula sheet? You know what's better than making a formula sheet is knowing that one already exists out in the wild. So I don't know. Maybe I didn't ever show you Paul's notes, but let me show you Paul's notes. Paul calc 1. Just give me a sec to have my browser not suck before I. Okay, yeah. So right. New share browser. All right. So yeah, if you just type like Paul and calc 1 into Google, it'll be like the first search result that you get. So Paul, Calc 1, okay, this guy. So he teaches at some university called Lamar. All right. And then somewhere in here, everyone does see the thing, I think, right? Somewhere in here we have formula sheets. I forget where though. There we go. Yeah, homepage, and then you can just look at calc cheat sheets. So for him, he actually like, for whatever reason, he makes you like download it before you can actually open it. We can take the complete one. May as well take the full complete one. That's going to be too much information for you. It's going to include stuff in the second half of the semester where we start doing integrals, but let's open this guy up. And so I think you can see this. Yeah, so he doesn't break it into sections, but this is a pretty reasonable thing to get. Actually, I'm pretty sure like, yeah, when I learned calc, when I learned calc in high school, this was one of the things that I used to just memorize everything. Yeah, so for example, right here, you've got your common derivatives. Maybe zoom out a little bit. Yeah, there. So you just like stare at this thing, familiarize yourself with where all the stuff is laid out. You kind of, you'll see, you'll understand like how he's doing it. He's separating all the different sections into things. So we haven't gotten to implicit diff or to that. And I think probably everything afterwards is going to be after the first exam. But yeah, everything before is so far like, yeah, what we are going to cover. And I think this goes all the way up to, oh, this actually goes up to some Calc 2 stuff. All right. Yeah. Okay. So yeah, there we go. It's pretty useful to use. All right, other questions? When results for the exam, well, after the exam deadline is reached, I would guess that we would have like a week to do the grading. So this, yeah, so the exams are actually going to be graded by us TAs. Yeah, so then after a week, it'll be probably released, the scores. Okay. Other questions?
On my calendar, it says that I have to like take it at 7 tonight. Is like, do we have to, or is it you can do it at any time?
It's any time, and it's actually over a few days worth. You're given a few days to actually go through and solve everything. So you should follow what is said in the announcements that Craig Spencer has sent out. All the information is on the what is the thing called? Canvas announcement. Yeah, that scheduling thing is more for like in a usual semester we would actually like during an exam time we would actually go to like a specific room and take the exam. But here everything is very different, and you're given, I think, a few days, a whole weekend plus. Yeah.
So when I open it on Canvas, it's not gonna like have a time limit that I have to turn it in by, right?
No. I'm pretty sure it doesn't say anything like that. Right. Maybe I should check as well. Like I skimmed the announcement. I don't really remember actually. What am I sharing with you guys? Maybe I should stop that first. Yeah. Let's read it out loud. Okay. Exam 1 information. Okay. Yeah, so share the browser again. All right, so this is what I'm looking at. This is, I mean, he didn't email us anything additional to this. pretty much. So yeah, untimed take-home exam. There we go. And it's between that. So how many days is that? 2, 3. You're given 2, 3, maybe 4 days ish. Okay, and then you upload onto Canvas, and then we grade with speed grader or whatever it's called. And yeah. Did I send the link out with the old tests? No, I didn't. Actually, so I don't even know, I don't know how good it would be to actually use that. That's one of the things I tried to communicate with Dr. Spencer about. But I mean, if you want to look at that for additional practice, you can. And really, that's just you Google KSU Math Exam Archive. Like I don't bookmark this because I can find it really easily. But yeah, it's this URL. I didn't email it, but like I expect you to know how to use Google. So yeah. And then you just select the course we're in, which is Math 220, Calc 1, and you can look at these. Yeah, I don't know how actually, because this semester is all weird. I don't know how much he's modifying the structure of the exam. He might not be modifying it at all, but he said something about like the fact that he actively removed this information from Canvas. Okay. Yeah. Other questions? Okay. Question, derivative of that or something along those lines. Yeah. Well, that's okay. So that's just a specific example of. Now I'm sharing, right? Yeah. That's just a specific example of. Where did I put it? This guy, this rule. Okay. So what you're talking about is with the function f of x equaling x to the 4th power. Okay, you're being asked this and you're trying to take the derivative of that. Well, the way that it works is for the exponential function, you just recopy the whole function. And then you have a chain rule, which says take the derivative of the inner function. The inner function in this case is the x to the 4th power function. Like it's just x to the 4th. Take the derivative of that function for x cubed. And this guy is the chain rule. And that whole thing is your answer. Yeah. Okay. Other questions? Well, I mean, one thing I can say, it seems like maybe you guys didn't find enough questions. One thing you can do for A, yeah, let me do this first. So let me come back to this Paul's notes, because I don't know if maybe you guys don't know why I'm recommending this, but so because his notes are actually effectively a textbook with worked out calculations. So if you are not comfortable with any of the topics, just like find what that topic is, as long as you know what it's called. So for the problem that we were just talking about, this is exponential and logarithm. And then maybe you skip over all the various words, but then you get to like the problems, and here like actually these are too easy, aren't they? Yeah, these are a little bit too easy. What's the harder ones? I don't know. But like suppose this was hard for you, then you can actually like go through, by hand and like work alongside the textbook and make sure that you can do the calculation. It gives you even some practice problems. these really aren't that hard. Why is it like chain rule? Did I miss the section? Derivatives. Oh, it's chain. Oh, so maybe it's after chain rule. Yeah, or logarithmic differentiation. So yeah, so for the Calc 1 problems, he actually gives you some practice that you could do. So you can just like go through all the steps for number 1 and just make sure that you can follow along and understand how to do it. If you want even more additional help, he gives assignment problems where he doesn't give the solutions to. But in this case, like what you could do, assuming that there was enough time, is you could hop onto someone else's help hours and I don't know, have them help you verify like your work or something like that. Have them work through it with you. All right, so then yeah, so this is why I'm like mentioning the Paul's notes, is because it's pretty useful. Back to the 4a, I guess. So someone asked about problem number 4a. I'm guessing that's homework 5. 4a, wait, 4. Yeah, 4a. So, right, when you stare at this function, you realize you have x in the base, x in the exponent. So you can't use the other two rules. You can't use power rule. You can't use exponential rule. You're forced to use logarithmic differentiation in order to differentiate this function. So the way that this works is you give the whole function a name. I usually use the name y, and then you take the log of both sides of this equation. So ln of y on this side, and then on the other side, the log is going to pop the exponent out. So we have 2 sine x outside, and then we have the ln of x there. And what's nice is that this is just a product rule now. So we are able to differentiate this whole equation. We get that, we get this just from product rule. And then as your very last step, what you need to do is solve for the y prime. So you multiply both sides by y, and then you substitute back what y actually is. So here y is what we named it, x to the sine of x, or x to the 2 sine of x. And so that's why this shows up here. This is y multiplied by everything that we got from the right hand side. And so that's how we do that. Yeah. Other questions? Product rule. Okay. Yeah. Yeah. Yeah, I don't know how much time you actually have before. So the exam is released at 5, right? So you have 4 hours. And it's also weird because like you don't technically need, since the cutoff deadline is not precise, like you kind of can just study things simultaneously while you're taking the exam. So it's kind of weird. I mean, you should know how to Google for various things. So like otherwise I would recommend like Khan Academy also gives you like these, it randomly will generate problems that are pretty good for practicing off of, but in this case it's, the point is a bit moot, I guess. All right, other questions? Like if you want, we still have 20 minutes. You can name like some topic, and we could try to find a few problems that are a bit challenging, go through them. So we might be doing things like limits, continuity, and of course the differentiation stuff.
Could we do more logarithmic differentiation problems?
Okay, yeah, sure. Let's take a look at some of these then. I don't know if I like these so much, but yeah, we can. Okay. Yeah, so let's just let's go through the practice problems together. Why not? How do I want to do this? It might be easier for me to yeah, use the Epic pen thing that I never seem to be using. I have to share my full screen, and then we can work through it as long as the app boots up. Okay. So now you should be able to see me scribble. I don't want to use that color. So you can see me scribble. Okay. I think. Right. So let's go through these in order, I guess. Or well, I would actually like call out what problem you want me to do. Maybe we could do like one or two of them. After go through IVT. Yeah, yeah. Sure, I can look at IVT. So is there a particular problem you want me to do, or I could just, I'm not gonna do all 5 this time, I think, but I might be able to go through 2 of the problems.
Yeah, you should do like either 2 or 3.
2 or 3, okay, yeah. Let's do 3 since that's the most complicated looking one. And then, so notice also 4, 5 are for the other case. So 4 and 5 are where you have x in the base and x in the exponent. But here, this one is just because taking the log is going to simplify the powers. So we have this function h of t, and we want to then take the log of it. Okay, so ln of h of t. Is there a way I can make the radius a bit smaller? Is going to equal, and then when we take the log of this, we'll have, so 1/2 of the log of 5t plus 8 plus 1/3. Remember that all these square roots are powers. So I'm just remembering it's a power and then pulling the power out because of log. Ln of 1 minus 9 cosine of 4t. And then subtract off the, I'm gonna have to wrap this, 1/4 of the logarithm of t squared plus 10t. So we have that. And what I'll do here is now we take the derivative, okay? So yeah, from this step, we then take the derivative. It's a derivative with respect to t. And so here we'll get 1, I want to say 1 over h prime. So 1 over h of t, sorry, times h prime of t is equal to, and then I take the derivative of the right-hand side. That's going to give me 1 over 2 times the quantity 5t plus 8 times 5 plus 1 over 3, the quantity 1 minus 9 cosine of 4t. And I can tack on the, I'll tack it off to the side. So now I take the derivative of the inner function, this 1 minus 9 cosine 4t. So the derivative of this is gonna be, cosine becomes positive. So this will be 9 sine of 4t times an extra 4 because the 4t is an additional function inside of the cosine. So that is the derivative of this term. And then subtract off, do I have enough space? I think just barely, yeah. I just barely have enough space. So 4t squared plus 10. And then chain rule, I'm going to put above. So take the derivative of the inner function. That's going to be 2t plus 10. Wrap that in parentheses. Doesn't make a difference here, but yeah, it's just better to do that. All right, so now we've taken the derivative, and then the last thing is we would have to sub back. So in this case, I'm not going to write everything out, but the h prime is what the problem is looking for. And so we would have this h of t, which is what we would have to replace with that function there. And then we put a big set of parentheses, and then we take this guy and we just copy it down there. Okay. And then, well, you can also just double check in case you're ever uncertain of, oh, well, the page is gonna change, but we can just also then double check, see that what we get is effectively the same thing. So except that the stuff is sort of on top of each other. Yeah, but yeah, he simplifies some numbers, but otherwise you can kind of check and see that like I did get exactly the same thing that he did. Okay. Yeah, so that's that problem. Right. Afterwards, go through IVT. Sure. All right, so IVT, like, do you want a quick lesson on IVT? Is that what you're asking, or did you want me to work through a problem on IVT? Remember sections IVT problem. Okay, let's see if I can find a problem. Wait, can I just go to the whole calc one page? Yeah. What does this have for IVT? Okay. Practice problems, continuity based, limit properties, discontinuous. Okay, use IVT to show stuff. Great. So yeah, I found it. Yeah, I think I could do all of them. So yeah, which one do you want me to try doing? I can make this and erase the. There we go. So 13, 14, 15. Which one do you want me to do? So 13 is the easiest one to plug into, but otherwise I'll have to reach for a calculator. But you'll be able to see me do it with the calculator. Okay, 14. Great. All right, so 14. Let's see. So the hope of the IVT is that these numbers will actually give you what you're looking for. So here we want to get this w squared minus 4 ln of 5w plus 2. We want that to equal 0. We want to find a solution for this equation on this interval, right? So there should exist some w inside the interval 0 to 4 such that this equation holds true. That's what the whole problem is all about. And so yeah, the usual way we do that is we try plugging it in. So what I'm going to start with is I'm going to call it a name, w squared minus 4 ln of 5w plus 2. And let's see what happens when we plug in at the endpoints. So I don't know how challenging he makes his problems. There is always the possibility that he's going to make it slightly more challenging. Let's see, if I put 2 in, I'm going to get minus 4 ln of 2. Yeah, and if I put 4, I'm going to get 16 minus 4 ln of 22. Okay. So what you see is that this number is clearly negative, and then this guy is the only thing that I think I need to reach for a calculator to do that. That's fine. I have a calculator in handy. I have 2 of them in handy, but this one is all I need for this problem. 16 minus 4. Does this have ln or log? It has ln. Great. Ln of 22. Okay. So it gave me some decimal value, but I don't actually need I don't need the precise number. What I need is to know, is this number positive or negative? And here it's positive. So this guy is greater than 0. And once we have these two things, we know that IVT is going to do the trick. So when you phrase your answer for IVT, you have to first make sure that f, the function, is continuous. on the interval that you're sort of trying to figure out the problem for. And here it is, because it's just a bunch of continuous functions that are being done to one another. So subtracted and composed. Composition, addition, subtraction, multiplication, division. Well, division up to whenever the denominator equals 0. All of those things that you do to functions, if the functions are continuous, the resulting function is still going to be continuous. So we're good to go on that thing. And then these two properties indicate that you are going to get IVT is going to say by IVT, you're going to get that there exists a solution. I guess we could call it W, but I'm sort of reusing W too many times. Let me call it Z. There exists some value Z inside of the interval in question, 0 to 4, such that f of Z is equal to 0. So, and this is precisely what the problem is asking us to find. It's asking us to find the existence of this number that will make it equal 0. You don't need to find the actual value. All you need to do is to guarantee the existence of it, which IVT does. Okay, and we can then check over the solution. It should pretty much do exactly the same thing. Blah, blah, blah. He calculates things, but he gives you actual values. And then the thing is to note that one of them is negative, one of them is positive, and 0 is bounded between the two. Therefore, there is going to be some, he's using C for my Z, such that the equation holds. So that is the way that IVT works. Okay. So we have 6 more minutes. Anything else you want me to talk about? I think maybe for this recitation, I might just keep the recording, make it run over to 2 hours, and then my computer will just have to render the whole thing, and then I can upload it. I don't know if I sent it out in the email, but I should probably hide the scribblings. So I don't know if I sent it out in the email, but BPRP, right? Black pen, red pen. Oh no, that's not it. Yeah, Calc 1. So his Calc 1, various worksheets, and what's useful is that he actually records solutions and puts them on his YouTube channel. So like you can actually, maybe not this one, but definitely so actually these problems are a bit more challenging than your typical set problems. Like he goes out of his way to actually construct problems that are slightly more challenging, and you can see that, like, yeah, for this one he has videos for them for derivatives if you want to practice taking derivatives. Yeah, he's got things for that. He actually makes the multiple choice, but the multiple choice is actually a little bit challenging because it'll force you to try to simplify your answer to get it to match. And then you can always, he's linked to playlists on YouTube, so of him solving more or less the same problems. Yeah, so additional practice if you want to do that. Yeah. Okay.
And for the other one that you're showing us, do we just search like, what was it, Paul's math or calculus or something?
Paul and calc. Yeah.
Okay.
Mhm. I guess I'll just maybe I'll put in the description of the uploaded video. I'll just link to some of the things. Yeah. Well, if there aren't any additional questions, like yeah, you can probably feel free to leave at this time. This is usually I would probably end it here. Maybe I'll pause the recording as well.
Thanks.
There's my pause recording button. All right. So, exam one. Prep or review. Okay. So, what questions do you have for me?
I was just thinking to maybe just do like maybe like one or two problems of like maybe like one problem of like each section and stuff like that of that we've gone over just to like refresh everything would be my question. Can we do that?
Sure. Do you have particular questions picked out? Do you want me to try finding them?
Like my main questions and stuff like that would be kind of like similar questions to like this week's homework with the logarithms and stuff like that.
With logarithms.
Yeah.
Okay.
And
So
then
the
maybe some
logarithmic differentiation, is that what you mean?
yeah.
Okay. And you were going on to say?
I was gonna say just like I think for everyone it would be nice to just like have maybe like one question of like just like regular like chain rule stuff, product and power rule and like quotient rule and stuff like that.
I see. So yeah, practicing various derivative type things. Yeah, I mean we can do that, definitely. Yeah. So all right. Yeah, so let me share various things. So you'll see this in the recording, but the recording is going to end up being like 2 hours long since I'm sort of combining both sections this time around. But so I'll probably add into the description of this video, assuming that it gets uploaded to YouTube just fine, some of the various links that I've been handing out to the students. So in terms of implicit, where is that? Or logarithmic differentiation, right? So where is this section? Somewhere in derivatives. Here, and I can just grab some problems from here and we can just choose one to go through. So in the last section, we actually went through number 3. So it'd be better not to just redo that, but you can choose maybe 2 problems to go through for this section.
Are you asking us to choose one?
Yeah.
Oh, okay. Okay.
Choose from me.
So you said you did 3 already. We can do 2.
Yeah, okay, we can do 2. That sounds good. Yeah. Trash. All right. And I'm sharing my full screen, right? So you should be able to see me scribble. Is that right?
Yep. We can see it.
Okay, great. Okay, yeah. So number 2, well, we're given y is equal to this function, and we want to take the derivative of it. So notice that here we actually aren't forced to use logarithmic differentiation. We could just do a quotient rule, but let's go ahead and try and see if it works out nicely. So I'll take log of both sides. That's the process of logarithmic differentiation. So start by taking both sides, and then you get ln of the function sine of 3z plus z squared, and then minus 3 ln of 6 minus z to the fourth. Sort of writing on top of the line, which is not ideal. Okay, I think I did that right. Yeah. Okay, and then from this point on, we take the derivative, dz in this case, because our variable is with respect to z. And here we'll have a y, 1 over y times y prime for the left-hand side. For the right-hand side, now we just take derivatives. So let's see, oh, there should be an extra parenthesis there. This is going to give 1 over sine of 3z plus z squared. And then we do the chain rule, which says take the derivative of this inner function. So that'll be a cosine of 3z plus z squared. But then there's an additional piece where we take the derivative of its inner function, which is 3z plus z squared. So the derivative of that is going to be 3 plus 2z. So all of this is the first term differentiated. The second term, minus 3 over 6 minus z to the 4 times, I'll put the times there, and then this is a minus 4z cubed. That's what I am getting. And then the very last step, so I'm not gonna fully write it out because it's a bit doesn't require any real thinking. The last step is we multiply by y and we substitute it in. So we're given y is this, we would have to substitute that for this value here. And we would put all of this inside the big parentheses. And so that would end up being the final answer. And what's helpful about this particular website is he actually gives you solutions that you can check through and make sure that you did the calculation correctly. Solutions with showing all the work. So we can then see that this guy and then plus cosine over sine. So he rewrites that as cotangent, but that is the same exact function that I have here. This term is this term. And you can see I have a minus 12 or minus negative 12, so then we get positive 12 z cubed over. So yeah, my work is correct. You know, this is how you practice, is you hopefully find a set of problems with an associated set of solutions and you just make sure that you can arrive at the solution.
Quick question for the exam: would the answer that you put, would that be good, or would we have to like simplify it all the way out to like how the web page did it?
You do not need to simplify. No.
Okay.
Yeah. Yeah. Usually, like, the reason we tell you not to is because we don't trust your algebra, pretty much. So, like, it's like, unless you need a simpler version of the function for like later on calculations, in an unsimplified format, like, it's easier to just immediately see like what rules you're applying, because effectively when we grade this kind of thing, we're just checking like, did you use the differentiation rules correctly? Did you remember, here we don't use quotient rule, but did you remember quotient rule correctly? Did you get the chain rule stuff all correct? We're just checking your application of these rules. Yeah, the simplification is just algebra, effectively. Yeah. Okay. And then you also mentioned some stuff about like practicing various rules. So, I mean, I have one idea for how we would do that, which is that we let me hide the scribblings. I should probably just clear all the scribblings. I don't need these anymore. Yeah, so I don't remember if I emailed out Black Pen Red Pen's website, but the reason I'm calling him out is because he has these worksheets, so you think you could take a derivative with the video solutions. So he actually records his solutions and puts them on his YouTube channel, and they pretty much run through the problem sheets. So sometimes he changes some problems because like he's done this over multiple years. But yeah, so we could grab a few of the of the problems from his worksheets, and you can just sort of like run through them to practice. The only thing is that these are somewhat challenging, and I mean, for me to go through a whole problem sheet would probably take the rest of the recitation. So I don't necessarily want to do that. But you know, if you want to look at them and tell me which one you want me to try doing. Yeah. So I mean, yeah. And in this case, like because he's doing it in a multiple choice kind of format, you do maybe need to simplify some stuff just so that you can match up the solution. I don't know. What do you want me to do?
I don't know, I was just suggesting maybe like just doing like maybe one problem of like each of the type of rules and stuff like that. But I mean, my big questions and stuff like that is like, do we know like the format? Do you know the format of the exam and like how many questions are on each part of it and stuff? That's like my big questions.
Right. That I don't know. I haven't seen what the exam is going to look like. It could look very similar to how exams are structured in the past, but it could also not. I don't know if this division into 3 parts is just to make it easier for us graders, but that it like has no real reflection on the structure. I have no idea. I haven't seen it yet. So I'll find out when you guys do.
Okay.
At 5. Yeah. Yeah. I mean, yeah. In terms of rules, we could just try to do a few of these problems. I guess I can maybe skip around to the various problems that actually have the various rules involved. So, yeah, I can try to do like what strikes me as interesting here.
Okay.
If you have some time on your own, you can always just try as well. So I'm looking at number 1 because at least this one has a few things. It has a bit of chain rule, has a product rule. And so this problem is just asking to find S prime. And in this case, we would take the derivative of the first function times the second, and then plus first function times derivative of the second. And then you have to remember derivative of the cosine is negative sine, so negative sine of 2t, and then times a 2 because of chain rule. So here I've used product rule followed by chain rule inside of the second term. And then you can kind of match and see, does this match any of the functions that are given? Well, to make it easier to match, I might want to just simplify the other terms slightly. Cosine of 2t minus 2t cubed sine of 2t. And I don't see it yet. I think it's this one. I think it's B. Is it B? Yeah, it's B. Okay. So that one's pretty easy. See if we can do number 2 at the same time. It'd be nice if I could just use a different color. I should be using a different shade. Maybe I can use dark green. Okay. Yeah. So for this one, quotient rule, right? So and then notice like it's possible that we might need to do some trig simplification. That's fine. Y prime, wrong diameter. Y prime is equal to quotient rule is denominator times derivative of numerator. So this is going to give you minus sine, and then minus numerator times derivative of denominator. Derivative of denominator is going to be cosine, and this is all over sine squared. Okay. Well, if I simplify this a little bit, I'm going to get minus sine squared minus cosine x minus cosine squared x all over sine squared x. But note that these two terms that I'm pointing out, minus sine squared x minus cosine squared x, that's going to just be -1. So this, oh, it doesn't save my color choices. This is equal to -1 minus cosine x over sine squared x. And unless this matches something exactly, so it doesn't match d or e, so I can eliminate those. So what I have to do is I need to actually do some trig, know some trig rules. So 1 over sine squared is cosecant. So I'm looking for negative cosecant, and I see that here. And then minus cosine over sine is going to be cosecant cotangent minus cosecant cotangent, which is there. So I'm able to verify that the answer should be C for this problem. Okay. Just any questions? Did you guys follow that calculation?
Yeah, I followed it.
Good, good. Yeah, then I guess we can try to find something else. Let me clear my screen, I guess. So, yeah, so 3 is really easy. It's just you see that it's a power, use power rule. Take 3 derivatives, not so bad. Take 2 derivatives, not so bad. Just the quotient rule. I've already taught you that formula. Well, this one, yeah, maybe this one's worth talking about. So when you tackle this kind of problem, notice that you should rewrite. Oh, what? Why did it? I don't know. Maybe they're keyboard shortcuts. So, secant x squared, the function is raised to the 5th power. You want to rewrite that, because if you don't, I've seen very many times people take 2 derivatives simultaneously. They end up taking the power rule while at the same time taking the derivative of the secant function. And here you don't want to, and that will not give you the right answer. So we rewrite this so we actually see it's a composition of 3 functions. We first take the power rule, which is going to give me secant to the 4th x squared. Yeah, and then times, and then we take the derivative of the secant of x squared function. So that's going to be secant tangent. So secant of x squared times tangent of x squared. And this, you should treat this all as being one chunk. Okay, so derivative of secant is secant tangent. That gives me that chunk. And then the last thing is that we take the derivative of the x squared function, which is 2x. So all in all, this gives me 10x secant to the 5th. I can combine the secants. Secant to the 5th tangent. And then I can compare. And let's see, it looks like this guy. Looks like A. Yep. I'm pretty sure that's right. Okay. Yeah, not so bad. Again with this nonsense. Yeah, so 9 is quotient rule. 10 is also quotient rule, maybe with some simplification. I don't know. The other sheets will have slightly more complicated looking things as well, but I would recommend, okay, that you haven't got to that yet, or that. Yeah, but for practice, I would kind of recommend just finding a set of good problems and practicing them. So I think I covered most, if not all, of the rules. Is there anything else you want to do?
Not for me.
Okay. Anybody else have questions? Are you guys there? No questions? I did email saying like you guys should come with questions. We still have 30 minutes of this recitation.
I guess maybe go over some maybe we could go over some like limit stuff maybe. Like
Could.
the stuff from like the very first stuff that we were doing and everything like that with the graphs and everything, the limits.
So things like with graphs.
Well,
good.
like the limits and everything, and asymptotes, I guess, and the limit laws and stuff.
Right. I mean, asymptotes is more or less a visual thing. Limit
Yeah.
laws. I mean, I can re-explain this. I don't know.
Yep.
I mean, I can talk through limit laws as well, but yeah, unless I'm. Let's see if I can find a example calculation or something like that. Problems. One-sided computer. Does it give me a graphs or no? It sort of gives me graphs. Well, no, not really graphs, but it gives me in terms of functions. So I don't really like that. And behavior. Yeah, these are too annoyingly complicated. I don't want to graph things first. So, yeah. So I guess we can just talk about the idea. So you should remember, what are sided limits and what is a two-sided limit. So to have a two-sided limit, you need that both of the one-sided limits have to agree with each other. And so when we have a superscript with a plus, that means that we're approaching it from the greater than side, which is the right-hand side. So we call this guy the right-sided limit and this guy the left-sided limit. And then in this particular problem, we're forced to sketch this piecewise function. That way we can analyze things a little bit more easily. Otherwise, we could still get away without sketching it, but then we would be working with the precise functions themselves, and you'd have to write a little bit more basically. But yeah, so here from -2, that's over here, and then approaching from the greater than side is going to limit to the value 1. That's what that says. And then approaching it from the left-hand side, we get 0. So we have these two different values. Since they are different, that means that the two-sided limit doesn't exist. Okay. And of course, a limit and evaluation are never the same thing. Well, unless your function is continuous at that point. But yeah, so that's why C and D are not, or they shouldn't give the same value, but they do in this case just because it's not defined there. But overall, imagine that you had like a circle, a filled in circle, then it would be able to say that f at -2 would have some specific value, even though the limit would not exist there. What else? So yeah, two-sided limits, and you should know that continuity just means that the two-sided limit is equal to the evaluation. It's that statement that has 3 pieces to it, right? So you have a two-sided limit that exists, the plugging in exists, and that the two things are equal to each other. This is what defines being continuous at that point. It's all to like get rid of the possibility of there being a jump discontinuity or pointwise discontinuity. So once you have those conditions satisfied, then you can just you can smoothly draw your function without lifting your pen off the paper. That's the typical way we describe such a thing. Yeah, and then so for this function, it might be easier just to not look at the problem, but just look at the graph. So here, like you see, if we approach -2 from the left, we'd get to -infinity. If we approach from the right, we'd get to 3. If we plug in, we would get 3. Over here, and you see this is an infinite discontinuity. That's what we would call that. Here we have limit approaching from the left is 3, limit approaching from the right is 1, and plugging in is going to be -1. The two-sided limit doesn't exist because, well, the two sides give you different values, and this is called a jump discontinuity because there's a jump between the two-sided limits. And then 3, the limit from the left and the limit from the right both are plus infinity. So in this case, we would actually say that the two-sided limit is plus infinity. But since that infinity is not a number, we would consider this an infinite discontinuity. Okay. Yeah. And limit rules. Did I write them? I guess maybe I didn't write them. I can write them. Yeah, so I guess we try to systematically talk about how the limit laws work. So, so the first thing about the way that the limit works is that it's linear. The operation of taking the limit is linear. So I'm going to start to abbreviate this, but f of x, let's say I have a number k in front of that, plus or minus g of x. So the first law is this linearity property, which says that this guy space is equal to k times the limit as x goes to a f of x plus or minus the limit as x goes to a of g of x. So you see that, and maybe I should put a big set of parentheses around the full expression there. So limit will push through and it will split over terms. So it'll split over the plus or minus. That's like the first replacement that you do. And then the second replacement is you would have k times f of x. Well, where k is just some fixed number. You can always pull out these fixed numbers, these coefficients. So that's the other half of linearity. And then you have various things that, and this is where I'm going to start to abbreviate. So this is a limit as x goes to a, f of x times g of x. And it's just saying, okay, we can just take this as the limit of f times the limit of g. Okay, so limit is going to split over multiplication. And it's going to split over division as well. So limit behaves very nicely. It behaves kind of like the way you would hope it to behave. Very nice and simple. And it will, do you normally write it as split over powers? Well, I mean, I guess you kind of can. So yeah, so if you have f raised to some power, maybe I can say of x, but you can take the limit of the function f first and then raise it to the power. So in this way, it's like we're pushing it inside of that operation of raising to a power. And more generally, I want to phrase it like that. You can just push it into the continuous. Yeah, I think so. Yeah. So let's say that I have a limit, and here I probably do want to put some parentheses. So if the function, there's a condition that lets you push it into a set of functions that are like composed with each other. I think the restriction is that the function f has to be continuous. This one I'm kind of forgetting, but it's easier to see it in practice with like specific functions. But yeah, usually like you're passing the limit inside, you're passing it through the function f so that it directly applies to the contents inside of f, which is in this case g of x. Like this is a more general version of the previous function, the previous limit law. The previous limit law, like the external function, the outer function in this case is this raising to some power. I think those are all the limit laws. I'm not sure if I'm missing anything. I don't think so. Yeah, I think that's everything. Yeah. Right. Whereas, well, you know that derivatives will satisfy this first bullet point, but they're not going to satisfy any of the other things. That's, yeah. Yeah, limits, derivatives, and integrals, when we get to them, they all satisfy the property of being linear. They all split over things like of this form. What else do we do with limits? I don't remember. Algebraic simplification of things when you have to like use limit definition. I don't know. I think you guys are probably comfortable with that, right? It's all stuff from way back. Continuity, squeeze theorem, IVT maybe. I don't know. You guys have any other questions?
Could we go over like one problem from squeeze theorem and IVT each or whatever, or just like
Okay.
a question, one of the questions that asked for it on the homeworks that you have up there?
Yeah. Okay. Yeah, I can talk through that again. So yeah, squeeze theorem. I guess that's just this problem. Right. So the thing about squeeze theorem is that we need to find two functions that whose limit will equal each other, and that these two functions are bounding the limit that we're actually trying to calculate. So squeeze theorem always starts out with some function that we're trying to take the limit of, which in this case is here. And well, the key to making this work is that you need to know properties about the sine and cosine functions, namely that they're bounded between -1 and 1. Right? If you just graph the sine function, graph the cosine function, you see it's an oscillatory function that never goes above or below +1, -1. Right? And so we start off with this inequality, and then what we do is we multiply by the thing that will fully match the function. So theta to the fourth in this case. And usually it's going to be some function. It's usually like x to some even power. Usually we don't use theta, but we use x. Yeah. Okay. So yeah, multiply all three sides by theta to the fourth, and you get minus theta to the fourth, the function in question, and then theta to the fourth. And then if you take limits of the bounding functions, you get that they both give you the value 0. We're taking the limit as theta goes to 0, as per the question. And so, well, if this inequality is going to hold true everywhere, which it's supposed to, by the fact that this inequality holds true everywhere, this inequality has to hold true everywhere. And so in particular, it's going to hold true as theta goes to 0. That means that this guy must have the limit that is between 0 and 0. Namely, it must also equal 0. That's how squeeze theorem works. So yeah, that's how we do that. And if you wanted to write it in words, part B is more like the way that you would kind of do it. instead of this diagram here. Yeah, the idea in this case, it gives you the two functions, whereas in the previous we had to actually find the two, being the minus theta to the fourth and theta to the fourth. So here we're given it, and then we just take the two limits as x goes to 5. And since this is true for almost everywhere except for this x equals -5, really that isn't even a condition that's needed. But yeah, so since these two give you the same value, squeeze theorem is going to say, well, when you take the limit of w of x as x goes to 5 in this case, well, the two bounding functions are going to squeeze that function w so that it only can take the one specific value, namely 25 here. For IVT, well, usually what we do is we just try to plug the function in at the endpoints of our interval, and we hope that whatever we get is going to be some interval that contains the number we're looking for. So in this case, since we want this to have a root, we're looking for when this function is equal to 0. So we want 0 to show up in the interval. That just means that we need the evaluation at these endpoints to have one number be positive, one number be negative. Once we have that, 0 is forced to be inside that interval between a negative number and a positive. And so all that's required is we just do a calculation here. In this case, I plug in 0, I'm going to get a positive number. I plug in pi over 2, I get negative. And so 0 must lie between. Great. That combined with the fact that the function is continuous, we always have to check that. So the function is continuous. So yeah, these two facts combined with this f of x being continuous means IVT applies. And not only that, but that there is some value in this specified interval such that the function f of x will take on the value 0 that we wanted to show exists. So here I'm phrasing in terms of a value p. So p is the specific number on the x-axis that is guaranteed to be a solution to the function f of x equals 0, i.e. a root of this function. And yeah, 6 behaves very similarly. Okay. Other questions? Well, if there aren't other questions, then I guess we can end here today. This is about the same time that we would normally end recitation. So.
Thank you.